Hi there! Our task for this video is to prove the quadrilateral angle sum theorem, which tells us that in a Euclidean space, the sum of the measurements of the interior angles of a quadrilateral is 360 degrees. Notice the claim is that we are on a Euclidean space, and we are to show that for any quadrilateral on that space or in plane geometry, the sum of the measurements of the interior angles is 360 degrees. To do this, let us use this given figure here. We have quadrilateral DEFG with interior angles D, E, F, and G. And what we need to show is that the measurement of the colored angles here, say the measurement of angle D, the green colored angle, plus the measurement of angle E, the blue colored angle, plus the measurement of angle F, the pink colored angle, and plus the measurement of angle G, which is the orange colored angle, be equal to 360 degrees. If we could show this to be true, that would mean our theorem is also true. We need to show our two-column proof containing correct statements and valid reasons in a logical manner in order for us to arrive at this and definitely proving this a theorem. To do that, our first statement here is what was given. So let's try it here. Quadrilateral D, E, F, G has interior angles and since they are angles, let me use the symbol angle D, angle E, angle F, and angle G. Again, the reason for that is this is what is given. The next part of this proof is where we establish relationships that what we could draw with these interior angles that will arrive to this statement here. Still, there is also an option for us to construct something in this figure that is acceptable and may help us prove this statement here. I'm talking about this. I'm going to construct a diagonal line, a diagonal, and we all know what diagonal is. So we have diagonal line DF. Again, it's diagonal line DF connecting non-consecutive vertices D and F. So we have here DF. In that case, I'm going to connect it in this manner. Hopefully this is straight. Assuming my drawing is straight, this is by construction. In doing so, after we have made this diagonal, we have divided angle D into two different angles. We are not sure if they are equal, but we are sure that angle D is now divided into two different angles. So instead of using angle D, we could use angle EDF for this bottom angle here and angle GDF for this other part here, or the other way around in naming angles. This is also true to the pink colored angle on vertex F. So instead of just using angle F, it's now either angle EFD for this side or angle DFE, and for the other part, it's either angle DFG and angle GFD. These are consequences of this diagonal line. Let's just simply add it here to since this is still part of the construction, let's just simply say making angle EDF and angle GDF GDF for this angle here, right? And another pair of angle for this pink colored here. You have angle EFD and angle GFD. This is again the consequence of the construction made here. Why do we came up with this construction, and why is it that we have divided these angles here, where that angle is part of what we would like to show as well as the other angle at the bottom? Take note that there are no given measurements to any of these angles here. Also, we cannot say that the angles that were divided by this diagonal line are congruent. So what we are going to look at is that from our singular quadrilateral, we have made two different triangles. Okay, again, we have made two different triangles. Triangle DEF and triangle GDF or GFD if you would like to. So we are going to declare it here. We have triangle DEF and triangle GFD or GDF if you would like to, GFD. We could say here are triangles formed with vertices D, E, F, and G. We can just say this is by definition of a triangle. I like that. Once we have established triangles here from this diagonal line, we can look into the previous angle sum theorem, which is focused on triangles. Specifically, the triangle angle sum theorem, which tells us that the measurements of the angles or interior angles, or the sum of the measurements of the interior angles of a triangle is equal to 180 degrees. Hence, for statement number 4, let me move this up a little bit here, like that, in such a way that you can still see the figure at the top. Okay, for triangle DEF, we could claim that the sum of the measurements of the interior angles here is 180 degrees. That's actually the measurement of angle E here plus the measurement of this angle here, not necessarily angle F because we are only concerned with this triangle here, angle F, but since F is a vertex for both these two angles, we could name this as EFD. Measurement of angle EFD plus the measurement of angle here, not necessarily angle D because angle D is now shared by those two angles. Since this is the angle that we are concerned about, we could call it angle EDF or FDE. But to be fair with what we used here earlier, since we use AFD as shared here, let's also use EDF as stated in statement number 2. So the measurement of angle EDF is equal to 180 degrees. Let me repeat. Angle E, this one. Angle EFD, this angle here. And angle EDF, the bottom one here, EDF. These are all interior angles of this triangle, so they must have up to 180 degrees. The reason for that is the triangle angle sum theorem, which tells us again that the sum of the interior angles of a triangle is 180 degrees. This is also true for the other triangle formed, the triangle GDF, having the measurement of angle G, this one here, plus the measurement of angle GFD, this one here. This angle here, not necessarily angle F, but this only is a part of that, GFD. Since we also use GFD here, let's also use it here. Measurement of angle GFD plus the last angle here, which is actually GDF as shared in statement number 2. The measurement of angle GDF is also 180 degrees. Same reason, triangle angle sum theorem. Notice that we already have two statements bearing 180 degrees, but our goal is 360 degrees. That would actually mean that there is a way that we could actually combine both of them. That's just a hint. That's a hint for this process here. But let us show that to happen. Where do we go next? Looking at our equations here, we already have angle G. We already have angle E. We also have angle G. That would mean this is already okay, and that's already okay here. But where is now angle D and angle F? We need to know where are they so that we could also get their measurements and probably relate it later on to this situation. Let us try move this up a little bit. I'm going to add these two statements here so that this side here will reach 360 degrees and we are almost there already. So pardon if I'm going to make it like this. Statement number 5. Measurement of angle E plus the measurement of angle EFD plus the measurement of angle EDF plus, I'm going to make it plus here, plus this bottom equation, measurement of angle G plus the measurement of angle GFD plus the measurement of angle GDF is equal now. Okay, I added both left hand side. That would mean it's the same as adding this side as well, right hand side. This is 360 degrees. You can argue that this is under angle addition postulate, or you could just simply say addition property. Since we are adding equalities, this is equal to that, added to another equality, that would mean adding equations will result also to adding this side as well to 360 degrees. Again, we already have angle E, check. Measurement of angle G, check. And the left hand side now becomes 360 degrees. What's next? Notice this angle here. Statement number 6. Move this one up a little bit. We don't necessarily need for a figure, but I'm also going to bring it down if necessary. Notice these two angles, EFD and GFD. Again, angle EFD and angle GFD. If we're going to look at the figure, angle EFD is a part of this pink colored angle here. Angle GFD is the second part. In short, when we look at these two, angle EFD and angle GFD, they make up this angle here, the whole pink colored angle, which stands for angle F. In short, we could come up here with a statement saying that the measurement of angle EFD plus the measurement of angle GFD, again EFD, GFD, is equal to the measurement of a singular angle EFD, GFD, this angle here, which is angle F. That would mean angle F now appears on our equation. This is also true to this next situation, the measurement of angle EDF and GDF. EDF is here. EDF, this lower portion of the green colored angle. For GDF, that's here, GDF. That would mean EDF and GDF makes up the whole angle here, which is originally angle D. So we could write it here, the measurement of angle EDF plus the measurement of angle GDF is equal to the measurement of entire angle D. So we have angle D. In this case, the measurement of angle D is already here. Look, measurement of angle D, measurement of angle D. Angle E is already here earlier. Measurement of angle F also now returns. Measurement of angle G is already there. So it's almost there. But we need to come up with the reason for this. And the reason for that is the angle addition postulate. Okay, since we don't have much space here, I'm going to do the same thing here as what we did in the previous video. You have here the additional statements and the additional responses. So out from this one, look, EDF, the measurement of angle EDF and the measurement of angle GDF makes up angle F. So we can just simply write both of this into one. Okay, as well as measurement of angle EDF and GDF, these two makes up angle D. So the statement number 7 will go like this. So I'm going to show statement number 6 and 5 so that you will be guided for this statement here. So we have here, copying statement number 5, we have here the measurement of angle E. Okay, it's E. Now EFD and GFD becomes angle F plus the measurement of angle F. Okay, plus after this one you have EDF and GDF, which comprises angle D. So by substitution you have the measurement of angle D. So we're done with this because we just copied it. The 2 became angle F, this 2 became angle D. What remains must be copied here, plus the measurement of angle G is equal to the total. Okay, the total, which is 360 degrees. The reason for this is by simply using the substitution property, because we just simply use statement number 6 and substitute whatever relationship here to statement number 5 as we come up with statement number 7. And we are just almost there. We just simply need to rearrange this in such a way that it will be the same as what we would like to show. So we just simply have to add another statement. We rearrange it to measurement of angle D plus the measurement of angle E plus the measurement of angle F plus the measurement of angle G is equal to 360 degrees. And the reason for that is simply arranging terms under commutative property. This is now the proof that it's true in a Euclidean space, the sum of the interior angles of a quadrilateral is 360 degrees. This was made possible when we made this diagonal, and instead of looking at it as a quadrilateral, we have two triangles where vertices are the same with the original vertices of the given quadrilateral, and came up with different angles here, and looking with the triangle angle sum theorem to come up with this statement. This is the proof for the quadrilateral angle sum theorem, which states that in a Euclidean space, the sum of the measurements of the interior angles of a quadrilateral is 360 degrees.